computer. Okay, assalamu alaikum and good morning. So today we are going to continue with our theory, topic 25, which is Equilibria. So our last session, we were looking at partition coefficient, KPC, where partition coefficient is looking at the distribution of a solute being distributed between two liquids that are immiscible. Okay, so this solute does not necessarily have to be a solid molecule. It can be any particle as long as it is inert. That means it is the same form in one layer. When it moves to the other layer, it also remains in the same form. The way you write down the KPC expression is the same. You will start with the, sorry, it's not connected. You will start with the solute dissolve in one solvent, and then the product will be the same solute dissolved in another solvent, okay, as you can see here. So usually on the left side or on the reactant side, it is the bottom layer, the solvent with the heavier density. And then on the product side is the top layer, which is the solvent with the lighter or lower density. It has to be the concentration at equilibrium, okay? So some question will only give you the number of moles or the concentration initially, but you have to find the concentration at equilibrium, which is what we have been doing for the last two questions. Okay, so now we are going to do example 9.3. So we first read the question together. Oleocanthal Q is a natural compound. It has antioxidant and anti-inflammatory properties. Okay, so that's the structure of Q, right? When 40 centimeter cube of hexane, okay, so 40 centimeter cube of hexane was shaken with 10 centimeter cube of a solution containing 0.25 grams of Q in 10 centimeter cube of methanol. Okay, so first things first, you need to identify your solute. Okay, so in this case, Q is your solute, and your solvents, your layers, would be hexane, layer 1, and methanol, layer 2. Okay, so in this case, you don't have aqueous layer. So it makes you think which one is in the bottom layer and which one is in the top layer. Now, for most cases, they usually accept either one. Okay, you can put your hexane at the bottom layer, or you can put hexane in the top layer. It doesn't matter because KPC is a ratio. So your answer, whether you put it either way, where you put your layers, will still give you the same, different, numerically different, but the ratio will still be the same. Okay, so you've already identified your solute. You've also identified your solvents. Let's continue. It was found that 0.060 grams of Q was extracted into hexane, sorry. Now, another term that I want to explain to you is the term extracted. Okay, so what it means by extracted is that after shaking, okay, so that means this is initially, right? I will show you in the form of a diagram later. 0.060 grams of Q was extracted. That means another word for that is 0.060 grams of Q was found in the hexane layer. Okay, so that's what it means. So please make sure you copy that down. Extracted means how much of Q has been found in that particular layer, in this case in hexane. Okay, so we will start with drawing the diagram first. Okay, in the exam you don't have to draw the diagram, but for your notes I want you to draw your diagram, because then it will help you understand if you come to revise this later. Okay, so here's what we're going to start with. Initially, we have a separating funnel. Okay, and it says that 40 centimeter cube of hexane. So I am going to start with hexane to be my bottom layer. Okay, it doesn't matter. Was shaken with 10 centimeter cube of solution containing 0. Methanol. 10 centimeter cube of methanol, and you've got your Q in the layer of methanol. Okay, and the amount of Q that you have is 0.25 grams of Q. Okay, and so that solute is your Q, right? Initially, you do not have any solute, any particles of Q in your hexane layer, okay? And then after this process called extraction, okay? After extraction, that means after shaking or after mixing at equilibrium, here's what happens. I am going to copy this whole thing. And paste it. Okay. It was found that 0.060 grams of Q was extracted into the hexane. Okay, so that means now some of the particles of Q have moved to the hexane layer, and it was found that you have 0.060 grams of Q. So automatically, because you now have some Q particles leaving the layer of methanol, the mass of Q in the methanol layer would decrease. Okay, it's no longer 0.25 grams. Okay, calculate the partition coefficient of Q between hexane and methanol. Okay, so I've got my diagrams here, and before working out the KPC, I need to write down the equilibrium equation, where my solute is Q dissolved in hexane is in equilibrium with the same solute Q in methanol. Okay, so I already know the volume and the mass of my Q in hexane, so I can find the concentration from there. I also know the volume of the methanol, but I don't know the amount of Q in methanol. I don't know the mass of Q in methanol. Okay, but I do know that I started with 0.25 grams of Q at the start of the practical. Okay, and then after that, they are being distributed, although not equally distributed. Okay, so that's why I need to find, I cannot just say, oh, 0.25 grams is divided by 2. So half goes to hexane, half goes to methanol. However, because you know the initial starting mass of Q and you know how much have gone to hexane, you can find the mass of Q that stays in methanol. Okay, so you can do that by doing here Q initial is equals to Q in hexane plus Q in methanol. So you can use this for mass, you can use this for moles, you can use this for not concentration. Okay, so only mass and mole. So initially you start with 0.25 grams of Q, and then at equilibrium, after the process of extraction or mixing, you've got 0.060 grams of hexanol. Therefore, you have to find the mass of Q in methanol. Okay, so can you please do that for me while I find my calculator? Okay. Is the mass of Q in methanol 0.19 grams? Did you all manage to get that? So then I can fill in that information, 0.19 grams of Q. Okay, before I write down my KPC expression, I also need to find the concentration of Q in hexane and the concentration of Q in methanol. Now, since both are in grams per centimeter cube or grams per dm cube, they will cancel out later on, okay, because they are a 1-to-1 ratio. So conversion is not necessary here, okay? So you can always use the concentration to be mass over volume. If you want to convert your mass to moles, you can, but that's just additional step. Okay, imagine turning your mass into mole and taking into account of the MR of Q, which is just a waste of time. Okay, later on you will see in KPC they will cancel out just nicely. Okay, so can you just take the mass of your Q in hexane to be 0.060 over 40 centimeter cube. I'll just leave the units first so you can see that they cancel out nicely later on. The concentration of Q in methanol is 0.19 grams over the volume, which is 10 centimeter cube. Okay, and KPC, your KPC has to be in the correct order. Top equation is Q in methanol over concentration of Q in hexane, which is 0.060 grams over 40 centimeter cube divided by 0.19 grams over 10 centimeter cube. Okay, so if you can see that they actually cancel out, so it doesn't matter the unit here, okay, as long as it's either mass or mole over the volume. Okay, can you work out the calculation for me and then share your answer? Okay, anyone has an answer to share? Zero point 0.0789. Yes, that's right. I got that answer too. Thank you, Ridwan. 0.0789. And there's no unit. Okay, no unit because the concentration terms will cancel out with each other. Okay. Right. I will now move on to example 9.4. So if you're done and you managed to get the answer 0.0789, please read the next question. And I will just leave this slide on for 1 more minute. Okay. Let me just okay. Right. Continue to the next question. When 20 centimeter cube of ethoxyethane were shaken with 75 centimeter cube of an aqueous solution containing 5 grams of an organic compound J. In 75 centimeter cube of water, it was found that 2.14 grams of J were extracted into the ethoxyethane. Okay, so first we need to highlight our solvents and our solutes. 20 centimeter cube of ethoxyethane, that is our solvent. We're shaken with 75 centimeter cube of an aqueous solution of an organic compound J. So our second solvent is aqueous solution, which is water. Okay. Solvent 2 is water containing organic compound J. That means J is our solute. Okay? So it is extremely important for you to correctly identify who your solvents are and who is your solute. So I will start with, again, another diagram. Initially, at the start of the reaction, I start with a separating funnel again. Okay, 20 centimeter cube of ethoxyethane and aqueous. So I'm going to put my aqueous layer to be at the bottom. Okay, so that's my aqueous layer. The volume and the top layer is ethoxyethane. And volume of ethoxyethane is 20 centimeter cube. The volume of the aqueous solution is 75 centimeter cube, and it contains 5 grams of solute J. So that means initially all my solutes are in the aqueous layer and none in the ethoxyethane layer. Okay, and then after extraction, same thing. Extraction means after mixing them and then distributing the solutes between the two layers, you will then reach an equilibrium where the solute J has spread between the two layers. Sorry, wrong, not color. Copy. Okay, and it was found that 2.14 grams of J were extracted into the ethoxyethane. So that means at equilibrium, I have some of my solutes moving into the ethoxyethane layer. Okay, and it was found the mass to be 2.14 grams. That means my if J in the aqueous layer has now changed. Okay, but that's not a problem because you know that J initial is equals to J ethoxyethane plus J aqueous. You started with 5 grams. At equilibrium, you have 2.14 grams of J in ethoxyethane, and you want to find J in the aqueous layer at equilibrium. So that should be 2.86 grams. Okay, please correct me if I am wrong at any point in my explanation. And of course, before you write down the KPC expression, you should start with the equilibrium, where J is your solute and it is in equilibrium with the aqueous layer and the ethoxy ethane layer, okay, which I have shortened it to be ETH. Kpc is equals to the concentration of J in ethoxyethane over the concentration of J in aqueous layer. And of course, if you are confident already, you can just sub in everything straight into the equation where your concentration of ethoxyethane is mass over volume divided by the mass of J in aqueous, which is 2.86 grams over 75 centimeter cube. Okay, where in this case, concentration is in grams per cm cube. Okay, you have seen concentrations in mole per dm cube, grams per dm cube, now in grams per cm cube. And why is it okay for us to not convert it? Because eventually they will cancel out. The grams will cancel out with each other, and the volume cm cube will also cancel out with each other. Okay, so can you please tell me the answer to that once you get it?
2.81.
2.81. Okay, let me just check. Thank you, Alicia. Is that you?
Yes, Miss.
Thank you. Yes, my answer is also 2.81 and no units. Okay, so I will leave this slide on for 1 minute. For those of you who's done with that, we'll move on to example 9.4, only 9.4, well, to the next question and start reading. Okay. Thank you, Ridwan, for your answer in the chat box as well. Okay, next one, I think, is 2 times extraction ataupun 2 times washing. It means the same thing. If you see the word extraction, washing, or shaken, it means the same thing. You are mixing the 2 layers, but because they are immiscible, it will be separated. Tapi the solute is already being distributed or partitioned between the 2 layers. Okay, let's read. In a new experiment, apa ni? Sama ka ni? Oh, okay, all right, sorry. It's a continuation. Okay, in a new experiment, 10 centimeter cube of ethoxyethane were shaken with 75 centimeter cube of an aqueous solution containing 5 grams of J, and the layers were separated. Okay, so this is actually a continuation. Okay, so continuation of the first question. I think you know this already because in your notes it was printed together, but for me it looks separated. Okay, so let's start with a diagram. But bear in mind, you know that the KPC, this is the most important. The KPC is the ratio of distribution of J between ethoxyethane and the aqueous layer. The number is 2.81. Okay, so let me just copy this information so that we don't forget them. Here. Okay, and for this equilibrium, I know that the KPC is equals to 2.81. Okay, now I move on to the new experiment where I have, oops, I have a new separating funnel. My drawing is getting better and better. Okay, ethoxyethane shaken with aqueous solution, right? So my aqueous solution will still be the bottom layer. I now have 75 centimeter cube containing 5 grams of J. Okay, same thing. I have J and that is 5 grams of J. My ethoxyethane is 10 centimeter cube and that is my ethoxyethane layer. I don't have any solute, 0 grams, okay? Okay, they were shaken and the layers were separated. Okay, so that means initially and then shaken after first shaken first time. Okay, and then I should have the same system, copy, paste, but this time I know that some of my solute has moved to the ethoxyethane layers. And I know that for this system, the KPC is 2.81. Okay, remember from the first part of the equation, if I shake them and they are in equilibrium, my KPC is 2.81. The layers were separated. Okay, so now I separate the layer. Okay, I have, so I will just draw a new separating funnel. I hope I have enough space. Oh gosh. So this is the ethoxyethane layer, and this is the aqueous layer from the first shaking or the first washing. Okay. Okay, I'm taking a lot of space. Okay. The aqueous layer was shaken with a second 10 centimeter cube portion of ethoxyethane. Okay, so that means this is my aqueous layer. Sorry. If you notice that after the first shaking, the mass of J in my aqueous layer will not be 5. It will be something less than 5. Okay. So then I will take this aqueous layer, 75 centimeter cube, but I don't know the mass of J. Okay. I mix it with a second 10 centimeter cube portion of ethoxyethane. That means I add a fresh solution of 10 centimeter cube of ethoxyethane that doesn't contain any J at all. Okay, you notice here, this is my first addition of ethoxyethane and I separate them. So then this ethoxyethane is 10 centimeter cube and it contains a certain amount of J. Okay, but this layer, if you read the question, I don't need it anymore. Okay, so my focus is now on this aqueous layer where I add a new fresh solution of ethoxyethane. Okay, and then I shake them. So after shaking, I should have, so at this point, you can say discard it. So you don't need to deal with that ethoxyethane layer from the first washing. Okay. Okay, just bear with me first. After shaking the second 10 centimeter cube portion of ethoxyethane and the layers were separated. Okay, the two organic layers were combined. Okay, oh gosh. This is a really complicated question. Okay, so I will take this and copy, paste. Oh gosh, it needs to be smaller. So I will call this second washing or second shaking. Okay, are you all still with me? Okay. I know you're probably lost at this point, but just bear with me. So initially, there's no solute in the second portion or the new layer of ethoxyethane. After shaking it, I will have some, and the amount of solute in aqueous will also decrease even further. Okay. So now I have J in my ethoxyethane layer. Okay. So the question is now, the two organic layers were combined. Oh, okay. The two organic layers were combined. Sorry, Artinya. This one is not discarded. My bad. We still need this because ethoxyethane is the organic layer here. So this is one of the more difficult questions that you will have to deal with. Okay, so don't throw that ethoxyethane layer because this is your organic layer. Okay, when it says the two layers were separated and then the two organic layers were combined, that means after this process, you separate the organic layer and you separate the aqueous layer again. And this organic layer that you have separated, you will combine it with the first organic layer in this stage. Okay, so that means I should draw another one. Sorry. I should draw another one. You separate. There we go. The ethoxyethane layer and the aqueous layer. Okay. So I'm going to use green for the ethoxyethane and purple for the second aqueous layer. Sorry, not organic. It should be aqueous. Okay, so this is actually what's happening. All right. Before we do the question, we go through again the question alongside with the diagram. Okay. Right. In a new experiment, okay, so this is our new experiment, 10 centimeter cube of ethoxyethane, that's this layer, were shaken with 75 centimeter cube of an aqueous solution containing 5 grams. Okay, so that's this layer, aqueous. The layers were separated. Okay, so this is what happens after shaking. Initially, there was no J solute in the layer of ethoxyethane, but after shaking, there will be some particles, okay, some amounts, but we don't know the amount yet. After the first shaking, we separate the layers. Ethoxyethane is isolated, okay, and then the aqueous layer is then used for the second time. Okay, this is now the second bullet point. The aqueous layer is shaken with a new 10 centimeter cube of ethoxyethane. Okay, these two are not related. The reason is because the purple ethoxyethane contains some solute of J. This one, initially, it has no solute of J at all. Okay, and then of course we mix them. After mixing it for the second time, we call this the second washing or the second shaking. You will see that the J solute has been distributed to the green ethoxyethane and also the aqueous layer. Okay, and then after the second washing, the layers were separated. Okay, the layers were separated. We separate the ethoxyethane and the aqueous layer. The two organic layers were combined. So remember the first organic layer from the first washing and the second organic layer, which is your ethoxyethane layer, from the second washing. Okay, so you want to combine these two later on, and then they want you to calculate the total mass of J extracted by this procedure. Okay, right, and then we do the calculation. So you see here, initially 75 centimeter cube and 5 grams of J. If you notice the first part of the question, it is the same value. 75 centimeter cube, you start with 5 grams and you use 10 centimeter cube of ethoxyethane. Because the system is the same and the ratio of partitioning them is constant, that means every time you mix ethoxyethane and aqueous with a certain amount of J, the ratio will always be 2.81. Okay, so that means from your previous question, from your previous part of the question, when you mix, it's not the same, is it? 20 centimeter cube and 10 centimeter cube. Oh, in the sama. Okay. Right. So, but you know that the ratio of KPC is 2.81. That means you can use the expression KPC, concentration of J in ethoxyethane, over the concentration of J in aqueous is equals to 2.81. Okay, so we are going to work out for the first washing first, or first shaking. Right, we want to know the mass that goes into the ethoxyethane and the mass that goes into the aqueous layer. Okay, so you can see that there are two unknowns here. Okay, but the volume, we know the volume. So because there are two unknowns, we need to let mass of J in whichever aqueous layer to be X. Okay, if the mass of J in aqueous layer is X, the mass of J in ethoxyethane will be 5 minus X. Do you all agree? Because J initial or J total is equals to J aqueous plus J ethoxyethane. Okay, so that means if J in aqueous is X, J in ethoxyethane is 5 minus X. Okay, so I will let you try to absorb that information first. We are now dealing with the first washing. We haven't moved to the second washing. Okay, once you are happy with this concept, you can now sub in the information. Okay, so you take concentration of J in ethoxyethane, which is 5 minus X, over the volume of ethoxyethane, which is 10 centimeter cube, divide by the concentration of J in aqueous solution, which is X over 75, is equals to 2.81. So you have to solve the expression. Okay, so that means 5 minus X over 10 times by 75 over X, which is equals to 2.81. Can you please help me solve that and give me the answer when you find them? I will do it manually on a paper. Okay, so I will just zoom out a little bit. I don't know if you can see that. Okay, let me check. Thank you, Ridwan. I am working out my value as well. X is equals to 3.64. Is everyone? Yes, Ridwan, we get the same answer. Thank you. So X is equals to 3.64. That means tadi my X was mass of J in aqueous layer. So I can fill in my details now. 3.64 grams of X in aqueous layer. Mass of J in ethoxyethane would be 5 minus 3.64, which is 1.36 grams. Is everyone okay? Okay, thank you, Alicia. So, what happens after this is that your layer of ethoxyethane is being separated, and that means in this layer of ethoxyethane, there is 1.36 grams of J. Okay, and your aqueous layer, which will be later used for the second washing or the second shaking, contains 3.64 grams of J. Okay, so now we move on to the second washing. Initially, there is 0 grams of J. Okay, so I will copy this slide, copy page. Okay, how do I do that? Duplicate. Okay, so I can erase this now. So first washing done. Okay, I now want to move to my second washing. Okay, I'll leave the diagram as it is. Second washing or second shaking. Okay, which is this diagram. Okay, I am still using the same solvent, as in it's a new fresh sample of ethoxyethane, but my system is still the same. It's between ethoxyethane and aqueous. Okay, so initially there's no J in my ethoxyethane layer, and there's 3.64 grams of J in my aqueous layer. That's from the calculation of the first part. Okay, and then I shake it. Of course, after shaking, some of my particles, some of my solute J have moved to the ethoxyethane layer. Okay, so now I do not know how much of J there is in my ethoxyethane and how much of J there is in my aqueous layer. But what I do know is that the KPC, the ratio of partitioning them, is still 2.81 because it is the same system. Okay, so what I can do here is that I can let the mass of J in aqueous to be Y this time. Okay, so the mass of J in ethoxyethane will be, now here you started with 3.64. Okay, you're no longer starting with 5 grams. So that means the mass of J in ethoxyethane will be 5, sorry, it's not 5, 3.64 minus Y. Okay, the reason for this is because J initial is equals to J aqueous plus J ethoxy. Okay, so my initial this time is 3.64 grams, no longer 5 grams. Okay. Okay. So I go back to the expression. Ignoring my first washing, I should now focus on my second washing. That means concentration of J in ethoxyethane is 3.64 minus Y over, the volume is 10, divide by the concentration of J in aqueous, Y over 75 centimeter cube equals to 2.81. So same process, you work out Y. Okay, so let's do that. I will try to zoom out at this until this point so you can see what's happening here. Okay, hope you can see. So there's a reason why we need that KPC constant. Okay. So someone please help me work this out and then we can compare our answer. Okay, hold on. My laptop is low bat. My iPad is also low bat. Okay, Ridwan has sent in his answer. Let me just plug in my answer is 2.65. Yes, Ridwan, thank you. We got 2.65. Y is equals to 2.65. That means if I go back to what my Y is the mass of J in aqueous. So I can say in aqueous, 2.65 grams. And then in ethoxyethane, it would be 3.64 minus 2.65. The answer is 0.99 grams. Okay, and then I separate the two layers. I have 0.99 grams, and here I have 2.65 grams. Okay. Okay. The question is now saying, calculate the total mass of J extracted by this procedure. Okay, the two organic layers were combined. So the two organic layers are this one, the first one, ethoxyethane layer from the first washing, and the ethoxyethane from the second washing. Okay. Maybe a different color. So total mass in organic layers. Okay, so your organic layers are your ethoxyethane is 1.36 plus 0.99 grams. .35 grams. And that is your ultimate final answer. Okay. Right. That is a lot of steps. Okay. For a question that has only 3 points, it looks short, especially the second part. But the process is long. Okay. I will leave this slide. I don't know if you can see it. I hope you can. For a bit, 1 minute, and then I will go through your instructions for APR. Okay, so what this process is telling you is that no matter how many times you mix your solute J with a new fresh sample of solvent, you will still have distribution. The solute J will be distributed into the two layers in the ratio of 2.81. So that's why this number is important, especially when you are doing more than one mixing. Okay, even your first mixing point, if you do your first mixing, your KPC is given to you, you are able to work out how much mass or amount have gone to layer 1 and how much have gone to layer 2. Okay, right. If you are ready and done with this drawing, please let me know.